Okay, so this is our final problem set, problem 5. And this is about evolutionary stability. So let's review again quickly the conditions for evolutionary stable strategies. And there are two. The first one is that whenever something is a strict Nash equilibrium, that is resistant to mutations. Because any mutation immediately will lead to a lower payoff or utility, and therefore the mutator will not accumulate enough reproductive fitness in order to establish themselves successfully in the system. The situation is slightly different with the second condition, and that suggests that a mutation that is played against someone who plays the incumbent strategy does not make the mutator worse off. So that is captured by the term UMN, so that the first is the payoff of the mutator. So the mutator does as good with somebody who plays the incumbent strategy as the mutator did before the mutation when playing the game with someone who also plays the incumbent strategy. So now what's important is the second condition, and that says if now someone who plays the incumbent strategy meets a mutator, but the one playing the incumbent strategy is still getting a higher payoff than someone who only plays with mutators, then the strategy is said to be evolutionary stable. I always find it difficult to put that in words, but I nevertheless tried. But when looking at the formulas, it should be much clearer. But anyhow, in words, one would say the first condition is that an incumbent strategy N is an evolutionary stable strategy if the mutant strategy M against the incumbent strategy has always a lower payoff than playing the incumbent strategy N against itself. Okay, it's still wordy, but that's the Nash equilibrium, the strict Nash equilibrium, and it still can be somewhat understood also in words. If you try to put into words the second condition, you would say something like, in case the mutant strategy does equally well against the incumbent strategy, the mutant strategy must earn a worse payoff when played against itself. So when everybody plays the mutant strategy, they must be worse off than somebody who still sticks to the incumbent strategy. Okay, let's take a look at this game. So we have two players, the car industry and the motorcycle industry. So let's first take a look at the best strategies are. So if the car industry thinks the motorcycle industry goes for combustion, then combustion pays a payoff of 8. So that's the car industry's best response. And if the car industry thinks that the motorcycle industry pursues electric, shall the car industry go with combustion? Yeah, that's 10. But also electric, that's also 10. So here we have the idea of a weak, or here we have the idea of weak dominance. And if the car industry thinks that the motorcycle industry goes for hydrogen, okay, then there's only one best response, which is to go also for hydrogen. Now let's turn to the motorcycle industry. If the motorcycle industry thinks that the car industry pursues combustion, then shall the motorcycle industry pursue combustion? And the answer is yes, because the payoff of 8 is bigger than 6. Oh no, that's actually wrong. There's a 9. That's the highest here. So then if the motorcycle industry thinks the car industry goes for combustion, then going for hydrogen has the highest payoff. 9 is bigger than 6 and 8. So if the motorcycle industry thinks that the car industry pursues electric, then combustion is 9, electric is 10, okay, so we can underscore this, and hydrogen is also 10. Those are the two highest payoffs or utilities. Lastly, if the motorcycle industry thinks the car industry pursues hydrogen, then combustion would be only 5, electric would be 8, but the highest would be also hydrogen, which is 9. Okay, so it looks like we have two Nash equilibria. That's also the first question. How many Nash equilibria are there? So there are 2. The two Nash equilibria are electric-electric and hydrogen-hydrogen. So what can be said about the incumbent strategy electric-electric? So let's begin. So we start by looking only at this Nash equilibrium. So that's where we start. And the question is, what happens if it's confronted with a mutation of combustion? Okay, so let's assume the mutator is the car industry, because if they go to combustion, well, they still get 10. So that means the first condition of the second condition is that the mutation played against somebody who is playing the incumbent strategy is still the same as the utility or the payoff that prevailed when everybody played incumbent strategy. And specifically, what we need to look at is the payoff here of 10. So the mutator gets here 10 and got in the other strategy 10. The payoff of the other one is for now not so important, but we just write it down. So here, then the other one gets 6, and here the other one got 10. Okay, so this is the first condition. Okay, so that may qualify for an evolutionary stable strategy, but now it depends what happens next if somebody who plays still the incumbent strategy N meets a mutator. Then the strategy is said to be evolutionary stable if the person that still sticks to the incumbent strategy gets a higher payoff than what the person or the player would get when playing against mutators. Okay, so let's see this one again. So let's erase the N. And so now we have to look at the incumbent. So this is still somebody who plays it electric, but now plays it against somebody who's playing the combustion. So we got to look into this area. Okay, so if somebody plays electric, the incumbent strategy in this equilibrium against a mutator combustion, so now that individual gets 6. And if anyone, if the incumbent would be better off if it played that strategy, the new strategy, with another who is adopting the mutation of combustion, because that would be 8. So this condition is actually not met. So here, if somebody sticks, basically what that says is somebody sticks to electric, then this player will fall behind somebody who's now only playing with other players that play the mutating strategies. So in other words, electric is not evolutionary stable, because the 6 is actually less than the 8. But for an evolutionary stable strategy to prevail, again, we would say, okay, if somebody mutates M, N, that is the same as U, N, N. But then, if somebody who plays the incumbent strategy against the mutator needs to get a higher payoff than somebody playing, so that condition is not met. You see, it is less, the 6 is less than the 8. So therefore, electric is actually not evolutionary stable. Okay. In other words, the mutation combustion will successfully infiltrate this mutation. And that is actually something that we can already observe in some countries where they said, you know what, this whole electric vehicle business, maybe we still should stick to combustion. Anyhow, the final question, what can be said about the incumbent strategy, hydrogen, when confronted with the mutation of electric? Okay, so now assume we are in an equilibrium of hydrogen. So we are here. And now somebody introduces a mutation of hydrogen. Let's take actually, somebody introduces the mutation of, what was it, electric, hold on, with the mutation of electric. Okay, so if the car industry decided to go to electric, that wouldn't be a good idea. They would immediately lose 3. But also if the second player, the motorcycle industry, went to electric, they also would lose immediately. So this is a clear indicator for a strict Nash equilibrium. So hydrogen is actually a strict Nash equilibrium. So that is evolutionary stable. So hydrogen is evolutionary stable because it's a strict Nash equilibrium. So that would be it. Okay, so that concludes the problem set on game theory, and I hope that was helpful to get an idea of how game theorists argue. So yeah, let's just stop here.